Uh, Hello, teacher, Dr. Garrido. We are presenting our final project, Deep Learning. We are team number 2, integrated by Bernardo and David Oliva. Okay, so what we did is a neural network for classification, 10 classes classification like MNIST, but focus in fashion. Can you go to the next? Okay, this is the outline of what we will be showing, the data description and motivation, why we use this dataset, the methodology that we follow to implement and develop this neural network, results that we got, the conclusions on how we can improve it further. Okay, why we choose Fashion MNIST? Fashion MNIST is a simple dataset. Is similar to the handwritten numbers MNIST. That's why it's called MNIST, and it is a balanced data. It has around 6,000 examples for each class, and it's easy to understand. So you just transform the image into a vector. It's a 28 by 28 black and white image. It has challenging classes because it does not just classify 2 of them like we normally would with sigmoid, but instead it has 10 classes as mentioned in the image below, above. Also, it has real life application. The ones that we came up with is to classifying the category of a product when you want to sell something in a e-commerce. Okay, so what we did. First, we did the pre-processing of our data, which is just reading the data and transforming it and normalizing it. And normalizing it just by dividing it by 255, which is the maximum value of an image. The model architecture is the wish that follows. It has an input of 784 units, followed by two hidden layers and one output layer. This GIF images tries to illustrate what we actually did, just converting the image into a vector and input it.
Okay. Hello, my name is David Oliva. So on the model training part, so once the pre-processing and the neural architecture is finished, the training process may start. This part is crucial because we provide training data to the algorithm. The training data must contain correct label answers, which is known as the target attribute to use to find patterns using the L layer model that we program. So it can predict new data that is not labeled. So there is a crucial part in this model training, a pair of terms called the bias and the variance. So in the model training section, it's important to take into account the bias, because if you have a high bias, it's also called underfitting. When you have a high error or low accuracy, it means that it doesn't fit the data. Your model doesn't fit it, so you need to decrease it. There are different ways to decrease it, like, for example, add more hidden layers, more neurons per layer, or you can do more time on the algorithm. So, for example, more iterations. And the problem with the high bias is a really fun example, that if you have, for example, 0.5 of accuracy, it's like if you're flipping a coin. So you are just doing a program, a random algorithm. So you don't want that. We want to have high accuracy. So be careful to have at least 0.75 accuracy. So, and then the other word, the variance, is almost not the same, but it's really have relation with the bias. If you have a high variance, it's also known as overfitting, is probably because you work really good with your training set, but really bad with your development set. So, so to check that, you need to you don't want an underfitting or overfitting. You want both to be like good. So you have to get a low accuracy, a low error and a high accuracy on the training set and the development set. So the accuracy must be really similar. Okay. So, and after that, we have the model evaluation. So to start with that, it's necessary to separate the whole data set in three different subsets that we mentioned before. There is the training set, the development set, and the test set. This maybe is split in three parts, but it must be most charged in the training sets. Like for example, 70% training set, 20% development set, and 10% test set. Or something similar. It's also valid to, you can randomly divide it in the three subsets. So as you can see here in the table number 2, we made some experiments, and the table number 3 that it's better to show it in the Jupyter notebook. Let's go to. Okay. Can you see it, Bernardo? Okay.
Yes, I can see.
Nice.
Okay. So first, in the Jupyter notebook as a Python script, you need to import all the libraries that you will be using. In this case, is NumPy, Matplotlib, and PyImage, and some functions that we modify in the file that DNN is _app_utils. So that's just the basically of the first cell. The second cell is where things get interesting. We have to import our CSV data, which was previously split in line 5 to 7. After that, we need to select the important input parameters. In this case, is pixel 1 to pixel 784, if I remember correctly. And we need the y. The y is just the label. In this case, is an integer between 0 and 9. In line 12, we just reshape it to be an image of a matrix of 28 by 28. And for the y, we just did a one-hot encoder, which is converting the number into a vector of the max value of y. In this case was 9, so it has 10 elements, if I remember correctly. And it's divided, the 9 in the index will be 1, and all the other values from 0 to 8 will be zeros. That's what we did in this part of the function. The second part is just showing what we actually have from the dataset. As we can see, the y is converted to a one-hot encoder, which is a class 0. In this case, is a t-shirt, and the image input. And just to verify that every shape of the values, all the variables are correctly located or splitted. And finally, we do a transformation from the image to a vector, as we saw in the GIF on the presentation, which is just every row of the image, concatenating it over the other, as in this slide. And that's why we get 784, which is 28 by 28. Can you go back to the Jupyter? And that's all that we did for pre-processing, also dividing it by 255, so we can have a range between 0 and 1.
Okay, so thank you, Bernardo. For the next is just the same as Bernardo said in the architecture model. And then here is the implementation of the L-layer neural network. We use different functions that are in the utils, initially parameters, model forward, compute categorical cost, model backward, and update parameters. So here it is. In this part, it was crucial to make different experiments, because this is a new kind of data set that we didn't see in class, like the cat or non-cat classification. This is a 10 items classification, so it was a little bit different. So here we can see the different experiments we did. For example, here we tried with 4-layer DIMs. The parameters, learning rate of 0.001 and 100 iterations. Well, you can see it didn't move. So here it was really bad. Then we tried with learning rate 0.05. Well, oh no, okay. With learning rate with 0.05 and the number of iterations 2050. And as you can see, the cost iteration, it was really bad. So we increased the learning rate. We changed a little bit the dimension layers. And here we have 1.28 and number of iterations 200. And well, here it was a little bit better, the cost. I mean, we always didn't have 2, now it's 1. And here, this one was the good one. It was with 4-layer mode and with learning rate of 3.2 and for 460 iterations. So as we can see, here's 1, and the cost after iteration for 160, it was 0.53, but I think it's 0.51 the 460. Here we can see the prediction training is 0.82. So we have well, basically low error. It's good. And the prediction with the development test. Well, I just want to make clear that we did this prediction training and prediction with the development set with all these experiments, but here and there are not. But in the PDF, Mr. Garrido, if you can see it, there are like here. There's different. Here is the training cost, the training accuracy, and the development accuracy of different experiments that we did. Here it was with different distribution of the training set, development set, and test set. And here with another, the one you recommend me in the office hours. So it was really good. So I also want to add that this was like a really systematically process. First, we did like with the hyperparameters that Mr. Garrido told us in class, and after that we start like thinking what will be the main problem about the low accuracy, and then we implement the idea, and that was going on and on. Okay, so let's get back. And with the prediction test, once we have like the best accuracy we could, we run with the prediction with the test set, and we obtain a 83% of accuracy. I think it's kind of well. And here we can see some print mislabeled images. I don't know. Can you see the zoom, Bernardo?
Yes.
Yes. Okay.
So
yeah, here's the mislabeled image. But I mean, what I want to make you see is that, for example, look, this 5th image. The prediction of is a dress, but the real class is a pullover. But I mean, even I would classify it as a dress. So I think the algorithm is really good to be a L layer model with just two activation functions. So okay.
So finally, what can we do to improve the performance of our model? Well, basically, right now we have just a fully connected layer, but there are many other layers that we can try. In this case, we saw an implementation with convolutional layers, which is more appropriate because it is an image instead of a vector, and it performs better than a fully connected. As we can see in the output of the Keras implementation, it has an accuracy of 0.91, which is actually pretty good, and the validation is 0.90. So what we can infer is that convolutional layers will perform better than dense layers in this case, just because it is an image.
Yes. Well, thank you for watching, Mr. Garrido. Hope you like the project.
Thank you. And this is the reference. Yep.